So it's been known since the late 1800s that bicycles are self-stabilizing, which means that if you take a bicycle without a rider and you push it fast enough, it will be able to coast on its own. And if it starts to lean in one direction, it will turn in that direction and effectively stabilize itself and continue to ride. When I was little, I called this ghost riding, and scientists have been trying to come up with a solution as to why this happens for quite a long time. For the first about 50 years that they were working on this problem, the leading theory was that the angular momentum of the wheels is what keeps the bike stable. And what this means is that you have a bike riding along. This is my picture of the bike. It's riding along with some velocity. And that means that both of these wheels are going to be rotating. And when you have a wheel rotating, you have angular momentum. And in this case, the wheels are rotating about counterclockwise, which means that their angular momentum, the net angular momentum of these both added up, is going to be coming out of the board. And due to conservation of angular momentum and the gyroscopic effect, if the bike starts to lean in one direction, thus putting a torque on the system, the wheels will try to counteract that torque. It'll try and conserve its angular momentum coming out of the board. And the theory was that that is what causes these bikes to be stabilized. A while later, scientists came up with another theory as to why bikes are self-stabilizing, and that has to do with trail. Now, trail is when the axis of steering points in front of the point of contact of a wheel. Most caster wheels have a positive trail, which means that if you imagine a shopping cart, they're able to rotate about some axis, and that axis is in front of the point of contact of the wheel and the ground. And what this does is that means that if you try to push your wheel system in one direction, the wheel will align itself so as to roll in that direction. Just like a shopping cart. You can easily just push it whichever direction and the wheels will follow. You may be thinking that a bicycle doesn't have a positive trail, but most bicycles actually do have a slight positive trail. And when I say positive trail, I mean that the axis of steering points in front of the point of contact of the wheel and the ground. So this is a quick drawing of a bike. This is the fork, thus the steering axis. And if you actually draw that point out, it hits this green dot, and the blue dot is the point of contact of the wheel, and you can see that it has positive trail. Now, these were the two theories as to why bicycles are self-stable, but what researchers at Cornell University have found is that the gyroscopic effect and trail effect are not the only things that cause bicycles to be self-stable, and you can actually build a bicycle that is self-stabilizing that has zero net angular momentum as well as zero or even negative trail. Right, so in order to prove that you need no net gyroscopic effect or trail in order to have a self-stabilizing bike, researchers have built what they call the two-mast skate. And all that is a bike. No, it may not look like a normal bicycle. It's a bike that has four wheels and no trail. So what happens is you have these two wheels that are in contact with the ground, and those roll forward just as a normal bicycle would. And you have two more identical wheels that are in contact with those wheels, but not in contact with the ground. And what that does is, while these wheels will rotate counterclockwise, that will cause these wheels on top to rotate clockwise. And since they're identical and they have the same moment of inertia, as well as the equal but opposite angular momentum, angular velocity, their net angular momentum will add up to be zero. As you can see, this wheel will have angular momentum pointing out of the board, and this wheel will have angular momentum pointing into the board, and they'll cancel each other. So that is how you have a bike with no gyroscopic effect. And what we have here is this is the steering axis. And the steering axis, if you plot it all the way down, points directly onto the wheel's point of contact with the ground, thus eliminating any effects due to trail. The two-mast skate that they actually built, they gave it a negative trail, just to make absolutely sure that trail has nothing to do with the self-stabilizing nature of a bicycle. And what they were trying to do with this model is they're trying to simplify the mechanics of a bicycle as much as they can. So they even made it so that you can adjust the center of mass of the bike, and that all of the mass of the bike is located at mostly 2 points on the bike. That's why it's two-mast skate. So you've got this point here and this point here, and these are connected up at the top. And I myself have tried to build a two-mast skate. It doesn't work as intended, but it was a good learning experience. So I'll go to explaining how mine works. All right, so here we have my interpretation of the two-mast skate. This should be pointing out this way. It was constructed completely out of wood, PVC, and a couple of caster wheels. It's completely bolted together, and you can take it all apart. I did have to make some changes to the system, obviously, to make it out of PVC. But I'll be going over each change that I made and how I constructed it. So let me just take off the front steering rig here. So this is the front steering rig. This is the steering axis. And initially I tried to have the steering axis point straight down to the point of contact of the front wheel. But what this did was it made it extremely hard for me to push. If you have no trail, then you know the wheel has no real reason to go where you want it to go. It can just kind of sit there and spin or go in the direction that you want for a little bit. Basically, I ran into a lot of problems with it, so I ended up giving this just a little bit of trail just to help out with being able to push it along and actually test it. So the wheels in here are caster wheels, and I've bolted the bottom one to the bottom of this board, and with the top one I've also bolted it, but I've given it a little bit of space down below. So what's actually happening in there is that this top wheel is just resting on the bottom wheel, and what that does is that allows both wheels to spin relatively freely, and it means that this top wheel will always be spinning with an equal magnitude and opposite direction of angular velocity with the bottom wheel, thus canceling the angular momentum of the system. And the rear wheel is exactly the same configuration, only there is no axis of steering. It's fixed to the frame. Now, something that I found with my initial design is it didn't have this this long sort of post coming out of here, and I was running into a lot of problems because something that they found that was necessary in order for there to be self-stabilization is that the bike has to be able to turn in the direction that it is falling. So if it's falling to the side like this, the front wheel has to be able to turn into the fall in order for it to self-correct. Similarly, if it falls this way, it has to be able to turn this way in order for it to self-correct. And with my initial design, I had the center of mass of this front steering rig directly on the axis of steering. And what that did was that if it was tilting in one direction, it didn't really have any reason for it to turn into that tilt. So there was absolutely no stabilization going on. When I realized this, I added this pole, and what this pole does is I can tape this mass onto this pole, and I can adjust its position, and I can adjust the mass, and thusly I can adjust the center of mass of this front steering rig. Right now I have it right here, so the center of mass is somewhere out here. And what that means is that when it starts to tilt to one side, this system will naturally try to lower its potential energy. And if the center of mass is right here, what it's going to do is it's going to swing that down, because as it swings down, it's actually lowering the center of mass, thus lowering its potential energy. And I made this weight sort of adjustable because something else that I found was important was the moment of inertia of this front steering rig side to side. If I put this mass out farther, you can see that it's got a larger radius and a larger mass on the end, and that gives it a larger moment of inertia, which would cause it to rotate slower naturally. And by bringing it in, I can give it a lower moment of inertia and allowing it to turn faster. And I found that this was important because if the ratio of the moment of inertia of this front steering rig, when compared to the moment of inertia of the entire bike, if that ratio is too big, then the bike won't be able to turn in time for it to actually self-correct. So what that means is that if this bike is able to fall faster, it's got a lower moment of inertia than it should, which allows it to tip over faster. If it can tip faster than this thing can turn to the side, then it will not be able to stabilize itself. So that's why I added the poles coming out of the top. What the poles coming out of the top do is that these poles give the entire bike a higher moment of inertia, thus causing it to fall over slowly, slower than it would, I guess, which allows this center steering rig to turn in time for it to self-correct. That being said, it still doesn't work, but I think that if it was going fast enough, it could potentially work. I'm going to show you some clips of it actually rolling in the hallway. And you can see how it starts to tip over, and you can see that it's starting to turn, but it just won't make it fast enough for it to be able to turn and actually correct itself and stabilize. So just really quick, I'm going to demonstrate the effect that trail has on this system. As you can see, I can sort of push this system along and it will follow whichever way I push it. The problem that I was running into before was that I would try to sort of guide it in a direction and it had no real reason to go that way. And the second effect that I'm just going to demonstrate really quickly right here is that if I start to tilt the rig in a direction, you can see it turns into that fall. That's it lowering its potential on the front steering rig. And that is essential in this case for the self-stability. Oh gosh, this thing is so loud. Don't worry, I designed it to break like that. Alright, so as you can see, it does not work, but that's okay. I ended up learning a lot about the stability of a bicycle, and I think the researchers, really had it right when they said that this is not a question that can be solved in any simple terms. There are a lot of factors that go into the self-stability of a bicycle, and it can't just be attributed to a gyroscopic effect or trail.